Good morning all. So we will start the question 5 by reading the question first. 6,530 mol per hour gas mixture, which contains 10% of the N-hexane and 90% of the nitrogen by volume at 2 atmospheric pressure absolute and 100 degrees Celsius, flows into a compressor which operates at constant temperature. Part A. Is the gas superheated? Justify your answer. So, in order to determine whether the gas is superheated or not, we need to find out its vapor pressure and also the partial pressure. We use the Ross law to find out the partial pressure of the N-hexane, which is equals to the mole fraction of the N-hexane times with the total pressure, equals to 0.1 times with 2 atmospheric pressure, and then we will get 0.2 atmospheric pressure. In order to convert the atmospheric pressure to the millimeter mercury, we times it with 760 millimeter mercury, and we can get 152 millimeter mercury. For the vapor pressure, we need to use the Anton equation. The formula of Anton equation is log vapor pressure of the N-hexane is equals to the A minus B over T plus C. From table before, we can get that A is equals to 6.88555, B is equals to 1175.817, C is equals to 224.867. So we substitute the A, B, C into the equation, and then we can get the vapor pressure of the N-hexane is equals to 18457.4 millimeter mercury. Since the vapor pressure of the N-hexane is greater than the partial pressure of the N-hexane, so the gas is superheated. Then we move to the question 5b. You are required to select one of the two suggested pressure, namely 19,000 millimeter mercury and 22,000 millimeter mercury, before the gas mixture have to be compressed at constant temperature in order to condense more N-hexane in the gas mixture inlet. What is the suitable pressure? Justify your selection. So, to determine which one is more suitable for the pressure, we need to find out the saturation pressure. How to find out the saturation pressure? We need to use the vapor pressure of the N-hexane that we find in the part A divided by the mole fraction of the N-hexane, and then we can get the P saturation is equals to the 18457.4 millimeter mercury. Since both pressure 19,000 millimeter mercury and 22,000 millimeter mercury is higher than the saturation pressure, so means that at both pressure the condensation can occur, but at higher pressure, which is the 22,000 millimeter mercury, is more suitable because it will condense more N-hexane.
Question 5C. Based on the question in Part B, answer the following question. Draw and label the process diagram completely. Do the degree of freedom analysis completely and conclude your analysis. So, the question given us 6,530 mol per hour of gas mixture is fed into the compressor. So we take the 6,530 mol per hour of gas mixture as the basis. And the mixture contains 10% of N-hexane and 90% of nitrogen at the pressure 2 atm and 100 degrees Celsius. So in the feed stream, we have 0.1 mole fraction of N hexane and 0.9 mole fraction of N nitrogen, and at the pressure 2 atm and 100 degrees Celsius. There are two outlet streams which are in equilibrium. So both of the streams are at the same pressure and same temperature. We use 22,000 millimeter mercury as the pressure because in part B we proved that 22,000 is more suitable as the pressure to condense more liquid hexane. So at the top stream we have N1 as the unknown for molar flow rate of top stream, and the Y is the unknown for mole fraction of N hexane, and 1 minus Y is the mole fraction of nitrogen. And the bottom stream is the molar flow rate of N hexane to be condensed in liquid. The unknown is N2. So we do the DOF analysis. There are three unknowns N1, N2, and Y, and two material balance, which are N hexane and nitrogen. One process spec Raoult's law. So 3 minus 2 minus 1, we can get 0, so the problem can be solved. Question 5C3. Determine the percentage of N hexane in the inlet stream condensed to be liquid. Without the calculation, evaluate the percentage if the pressure used is 16,000 millimeter mercury. Before we solve the percentage, we have find out all the unknowns first, and at the end we can solve the percentage. First, we use the Raoult's law. The vapor fraction equals to the vapor pressure divided by pressure. So the vapor pressure of N hexane is 1845.74 millimeter mercury and divided by 22,000 of millimeter mercury. So we can get 0.084 mole fraction of N hexane, and 1 minus Y is 0.916 is the mole fraction of nitrogen in the top stream. Then we use nitrogen balance input equal to output. We can solve the N1, which is the molar flow rate of top stream, 6415.94 mole per hour. Then we use N hexane balance input into equal to output. We can solve N2, the molar flow rate of N hexane condensed to be liquid. N2 equals to 114.06 mole per hour. Then we need to calculate the N hexane condensed to be liquid. So we use the molar flow rate of N hexane condensed to be liquid, which is N2, divided by the N hexane of feed stream, which is 0.1 times 6530. So N2 divided by the feed stream and multiply the 100%, we can get 17.47%. Then the question asks us if the pressure is 16,000 millimercury, what is the percentage of the N hexane in the inlet stream condensed to be liquid? So the answer is 0%. This is because the 16,000 millimeter mercury is less than the saturation pressure, which is 18457.4 millimeter mercury. The pressure need to be higher or greater than the saturation pressure 18457.4, so the process of condensation can be happen. If the pressure is lower than the saturation pressure, it will be not happen. So the condensed percentage of NHCN is 0%. Thank you.